19th International Physics Olympiad, year 1988. IPHO. Problem 1. Spectroscopy of particle velocities. Theory. Basic data. The absorption and emission of a photon is a reversible process. A good example is to be found in the excitation of an atom from the ground state to a higher energy state, and the atom's subsequent return to the ground state. In such a case we may detect the absorption of a photon from the phenomenon of spontaneous emission or fluorescence. Some of the more modern instrumentation make use of this principle to identify atoms, and also to measure or calculate the value of the velocity in the velocity spectrum of the electron beam. In an idealized experiment, see figure 19.1, a single charged ion travels in the opposite direction to light from a laser source with velocity v. The wavelength of light from the laser source is adjustable. An ion with velocity 0 can be excited to a higher energy state by the application of laser light having a wavelength of lambda equals 600 nanometers. If we excite a moving ion, our knowledge on Doppler's effect tells us that we need to apply laser light of a wavelength other than a value given above. There is given a velocity spectrum embracing velocity magnitude from v1 equals 0 m s to v2 equals 6000 m s. See figure 19.1. Questions 1. Part 1. What range of wavelength of the laser beam must be used to excite ions of all velocities in the velocity spectrum given above? Part 2. A rigorous analysis of the problem calls for application of the principle from the theory of special relativity v prime equal v by square root from 1 plus v over c divided by 1 minus v over c. Determine the error when the classical formula for Doppler's effect is used to solve the problem. Question 2. Assuming the ions are accelerated by a potential u before excited by the laser beam, determine the relationship between the width of the velocity spectrum of the ion beam and the accelerating potential. Does the accelerating voltage increase or decrease the velocity spectrum width? Question 3. Each ion has the value E over m equal 4 by 10 power 6 ampere seconds over kilogram. Two energy levels corresponding to wavelength lambda 1 equals 600 nanometers and wavelength lambda 2 equals lambda 1 plus 10 power negative 3 nanometers. Show that lights of the two wavelengths used to excite ions overlap when no accelerating potential is applied. Can accelerating voltage be used to separate the two spectra of laser light used to excite ions so that they no longer overlap? If the answer is positive, calculate the minimum value of the voltage required. Solution. Question 1. Part 1. Let v be the velocity of the ion towards the laser source relative to the laser source. Nu prime the frequency of the laser light is observed by the observer moving with the ion. For example, in the frame in which the velocity of the ion is 0, and nu the frequency of the laser light is observed by the observer at rest with respect to the laser source. Classical formula for Doppler's effect is given as nu prime equal nu by 1 plus v over c, formula 1. Let nu star be the frequency absorbed by an ion, characteristic of individual ions, and nu L be the frequency of the laser light used to excite an ion at rest, hence, nu star equal nu L. For a moving ion, the frequency used to excite ions must be lower than nu star. Let nu H be the frequency used to excite the moving ion. When no accelerating voltage is applied, we have next table. Here nu L less than nu H, nu L equal nu star. Calculation of frequency nu H absorbed by moving ions represented in formula 2. The difference in the values of the frequency absorbed by the stationary ion, and the ion moving with the velocity v delta nu equal nu H minus nu L. The difference in the values of the wavelengths absorbed by the stationary ion and the ion, moving with the velocity v delta lambda equal lambda L minus lambda H, which is using formula 2. We have v over nu star. Higher frequency implies shorter wavelength, and in this case we have lambda L minus lambda H equal 12 by 10 power negative 3 nanometers. This is the solution to question 1 part 1. Part 2. The formula for calculation of nu prime, as observed by the observer moving towards light source, based on the principle of the theory of special relativity, nu prime equal nu multiplied by square root, from 1 plus v over c divided by 1 minus v over c, where v is the equal magnitude of the velocity of the observer towards the light source. Nu prime is the frequency absorbed by the ion moving with the velocity v towards the light source, also observed by the observer moving with velocity v towards the laser source, and nu is the frequency of laser light as observed by an observer at rest. To put in a metaphoric way, the moving ion sees the laser light of frequency nu even though the scientist who operates the laser source insists that he is sending a laser beam of frequency nu. So nu prime is equal expression 1 and finally 2. The second term in the brackets represents the error if the classical formula for Doppler S effect is employed. So we see that V over C equal to by 10 power negative 5. And finally we have expression 3. The error in the application of classical formula for Doppler S effect, however, is of the order the factor 2 by 10 power negative 10. This means that classical formula for Doppler S effect can be used to analyze the problem without losing accuracy. That was solution to part 2 of question 1. Question 2. When acceleration voltage is used, we have lowest limit of the kinetic energy of ions is 1/2 mvl square, which is equal the charge of electron, E multiplied by U and VL equals square root from 2U over m. Highest limit of the kinetic energy of ions 1/2 mvh square, which is equal to 1/2 mv square, plus charge of electron E multiplied by U, and VH equals square root from V square, plus 2U over m. Spectrum width of velocity spectrum VH minus VL equal expression 3. Note that the final velocity of accelerated ions is not the sum of V and square root from 2U over m as velocity changes with time. In equation 3, if this square root is negligibly small, the change in the width of the spectrum is negligible. By the same token of argument, if this root is large or approaches infinity, the width of the spectrum of the light used in exciting the ions becomes increasingly narrow and approaches 0. That was solution to question 2. Question 3. Given two energy levels of the ion, corresponding to wavelength, lambda 1 equals 600 nanometers and lambda 2 equals 600 plus 10 power negative 2 nanometers. For the sake of simplicity, the following sign notations will be adopted. The superscript in the bracket indicates energy level 1 or 2, as the case may be. The sign prime above denotes the case when accelerating voltage is applied, and also the subscripts H and L apply to absorbed frequencies, and also wavelengths, correspond to the high velocity and low velocity ends of the velocity spectrum of the ion beam respectively. The subscript following lambda, or nu, can be either 1 or 2, with number 1 corresponding to lowest velocity of the ion, and number to the highest velocity of the ion. When no accelerating voltage is applied, the subscript 1 implies that minimum velocity of the ion is 0, and the highest velocity of the ion is 6,000 meters per second. If accelerating voltage U is applied, number 1 indicates that the wavelength of laser light pertains to the ion of lowest velocity, and number 2 indicates the ion of the highest velocity. Finally, the sign star indicates the value of the wavelength, lambda star, or frequency, nu star, absorbed by the ion, characteristic absorbed frequency, when no accelerating voltage is applied. For the first energy level we have next table. Differences in frequencies of laser light used to excite ions is nu H1 minus nu L1. Differences of wavelengths of laser light used to excite ions is lambda L1 minus lambda H1. This gives V over nu L1 star equals 0.012. Hence the spectra of laser light, absorption spectrum, used to excite an ion at two energy levels overlap as shown in figure 19.4. When accelerating voltage is applied, let lambda H1 prime and lambda L1 prime be the range of the wavelengths used to excite ions in the first energy level. When accelerating voltage is applied, note the prime sign to denote the situation in which the accelerating voltage is used, and let lambda H2 prime and lambda L2 prime represent the range of the wavelengths used to excite ions in the second energy level also. When an accelerating voltage is applied, condition for the two spectra not to overlap, lambda H2 prime equal or greater than lambda L1 prime. See figure 19.4. Expression 4. Keep in mind that lower energy means longer wavelengths and vice versa. From condition 3 we have lambda L minus lambda H equal V over nu star. Expression 5, lambda Ln prime minus lambda Hn prime. The meanings of this equation is if the velocity of the ion is V, the wavelength which the ion sees is lambda L, when lambda H is the wavelength which the ion of zero velocity sees. Expression 5, lambda Ln prime minus lambda Hn prime. The meanings of this equation is if the velocity of the ion is V, the wavelength which the ion sees, is lambda L, when lambda h is the wavelength which the ion of zero velocity sees. Equation 5 may be rewritten in the context of the applications of accelerating voltage in order for the two spectra of laser light will not overlap as follows, where n is the order of the energy level. Expression 6. The subscript L relates lambda to lowest velocity of the ion which sees, frequency nu star. The lowest velocity in this case is square root from 2 EU over m, and the subscript h relates lambda to the highest velocity of the ion, in this case is square root from v square plus 2 EU over m. Equation 6 will be used first to calculate width of velocity spectrum of the ion accelerated by voltage u, and second, to calculate potential u, which results in condition given by expression 4. Let us take up the second energy level, lower energy level of the two ones, of the ion first, lambda L to prime minus lambda h to equal v prime over v star. Expression 7, substitute v prime equals square root from 2 EU over m, lambda h1 equals 600 plus 10 power negative 3 nanometers. V star equal 5 by 10 power 14 Hz, v equals 0 meters per second. So lambda h to prime equals 600 plus 0.001, multiplied by 10 power negative 9 plus square root, from 2 EU over m divided by 5 by 10 power 14 meters. Expression 8. Considering the first energy level of the ion lambda L1 prime, minus lambda h1 equal v prime over v star. Expression 9. In this case v prime equals square root from v square, plus 2 EU over m, v star equal 5 by 10 power 14 Hz, v equals 6000 meters per second, lambda h1 equals 600 by 10 power negative 9, and lambda L1 prime equals 600 by 10 power negative 9 plus square root, from 2 EU over m divided by 5 by 10 power 14 meters. Expression 10. Substitute lambda h2 prime from 8 and lambda L1 prime from 10 in for 1, gets inequality 11, which means 500 greater or equal to expression 12 or expression 13. Assume that u is of the order of 100 and over, then we have next calculations. And finally we have u greater or equal 162 volts. The minimum value of accelerating voltage to avoid overlapping of absorption spectra is approximately 162 volts. That was solution to question 3. This concludes our discussion of the solution to problem number 1 at this Olympiad.